about the dynamics of rolling objects today, and more generally, we're going to talk about the dynamics of rotating objects. Yeah, I liked it. It was a cool video. I liked it a lot. So what we're going to do is we're going to build a relationship between rotational and linear motion in a very particular case. The case that we're going to be talking about is going to be rolling without slipping. So rolling without slipping, also known as perfect rolling, is an additional constraint or an additional condition on the motion of a system. And that constraint arises in a very particular case. So the question is, and you guys can probably imagine what rolling without slipping is. It's when something rolls rather than sliding, right? Rolling without slipping. So let's think about why this notion of rolling without slipping might be important. So right at the get-go, when two surfaces slip or slide past each other, we get that there's thermal energy that's created, which means that the mechanical energy isn't conserved. Rolling without slipping may include static friction, and that's how the rolling without slipping occurs, right? Like something round. There we go. Right. So if I have a ball and it's rolling, there's static friction, and the static friction is a result of, or the static friction causes the ball to rotate when it's, I know what it is. Is this better? Better or worse? Okay. Yeah, I'm using my cameras rather than my tablet. Right, so when it's rolling, there's static friction, and the static, so if the object's rolling, the static friction keeps it from just sliding forward. It causes the ball to roll. But static friction doesn't do work. And so there's no kinetic friction, so the mechanical energy is conserved. There's no kinetic frictional force, which implies that mechanical energy is conserved. Also, another nice feature of rolling without slipping is that the distance traveled is related to the total angle rotated. By the way, that little tilde means like related to. And so we can actually figure this out fairly straightforwardly, right? You have a ball, it rolls some distance. Let's just look at a point, right? And let's say that this distance here is r. That point, as it travels, it's like I don't know, I can't actually tell. It would end up like here, I think. That point is going to rotate around as it travels to the right. So if the round object rolls a distance x, well, we can figure out how much angle it rotated by. In this case, it rotated by an angle r times theta, where r is that r is that radius. Oops. Okay, I'll just erase both of them. Put that there. This is going to rotate around. And so we can actually relate the speed here to the rotational speed, because if we know that the speed is just the time derivative of the position, then the rotational speed should be the time derivative of the angle. And you guys already knew this relation, but this now tells us a relationship between the speed of an object and the rotational and the angular speed of that same object. So this is to say, when an object is rolling without slipping, the speed that the center of mass is moving at, or the speed that the axis of rotation is moving at, is related to the angular speed that the thing is turning at, which is a really useful constraint because it allows us to, say, relate the kinetic or the translational kinetic energy to the rotational kinetic energy, because in principle, you would need to know the rotational speed and the translational speed. But if you know one and you know it's rolling without slipping, then you can figure out the other. A good example of this that's not quite exactly an object rolling would be, say, a spool of rope unwinding. So if you have a spool of rope, try to make this so it looks reasonable. Spool of rope, meaning like it's just a bunch of rope wrapped around a thing. As the rope unwinds, the rate at which the rope is coming off would be related to the rate at which the spool rotates, right? By the same relationship. Because the point is that the translational distance that rope is covering is related to the arc length that it wraps around the spool. And assuming that the spool's radius doesn't change, this relationship would just hold up for the entire duration of the spool unwinding. So we'll see an example of a spool unwinding. We'll actually do that example later today if we get to it. But we're going to now start applying this notion of rolling without slipping. So let's talk about mechanical energy conservation. So hopefully all of you guys watched that Walter Lewin video. Super, super interesting. The dude is a great educator, and it'll be a shame when he dies, which will be eventually. And so we can now answer the question, or at least we can try to answer the question, why do the cylinders roll at the speeds that they roll at? Like, why is it that one of the cylinders rolled faster than one of the other cylinders? There's no friction, there's nothing happening. Like the exact same thing is happening to both cylinders. The same forces are acting on the cylinders because, well, at least they have the same acceleration due to gravity and so on. So we can answer the question using mechanical energy conservation, talking about rotational and translational kinetic energy. So for perfect rolling, we have to realize potential energy can be distributed into more than just translational kinetic energy. It can be distributed into both translational kinetic energy and rotational kinetic energy. Whereas before, when we just had an object falling and it wasn't, or sliding and it wasn't rotating, the only place the potential energy could go would be to the translational kinetic energy. Now we have two possible places that it could go, so it's going to distribute itself in both. The non-slip condition, also known as the perfect rolling condition or the rolling without slipping condition. The non-slip condition, VCM equals R omega, that's the relationship that we have here, determines how much goes where. And we're going to see that now. Right, you have so when you have a cylinder at the top of this this inclined plane, it has some amount of potential energy, and when it gets to the bottom, it has less potential energy. So that potential energy goes somewhere, and some of it will go to the translational kinetic energy because it's moving. Some of it will go to the rotational kinetic energy because it's rotating. We need to figure out how that extra potential energy gets distributed to those two, and it turns out that the rolling without slipping condition precisely determines that distribution of energy. In fact, we're going to find that the bigger the moment of inertia is, the larger the fraction of energy that the rotational kinetic energy gets. That kind of makes sense, but let's check by doing the math. So we have our inclined plane, say with an angle theta. Maybe it starts at height h and it goes down to height 0. So let's just call that distance that it covers vertically 0, and the ball rolls down the inclined plane, right? Let's say that or ball, cylinder, whatever it is. Let's actually call it a cylinder. Say it has radius r, starts off up here, ends down at the bottom. So we can use energy conservation, mechanical energy conservation, to figure out this problem. So typically we would write mechanical energy conservation as delta potential energy plus delta kinetic energy equals 0. But you guys have been doing this before, and we can always do this. You can split the before and after. So we can write the total energy on one side equals the total energy on the other side, i.e. potential energy initial plus kinetic energy initial equals potential energy final plus kinetic energy final. And if we choose our coordinate system so that y equals 0 down at the bottom and y equals h at the top, then the final kinetic energy is 0. Sorry, the final potential energy is 0. So let's just kill that right away. And the initial kinetic energy, we're going to assume it starts at rest, is also 0. So let's just start filling in. The initial potential energy in this coordinate system would be mgh, m being the mass of the object, of course, the mass of the cylinder. And then the final kinetic energy, well, it has two parts. It has translational kinetic energy and it has rotational kinetic energy. They're both measured about the center of mass. So the translational kinetic energy is 1/2 times the mass times the translational times the velocity of the center of mass squared, plus the rotational kinetic energy, 1/2 I omega squared. This is the moment of inertia measured about an axis that passes through the center of mass, passes through that point, the center of mass of the object, times omega squared. And that's the angular velocity of the cylinder as it's rolling. So we can use the non-slip condition to rewrite this. We know how to write omega in terms of v. That's what the non-slip condition gets us. So we have that mgh is equal to 1/2 m vcm squared plus 1/2 icm vcm over r squared. And then we can factor group. We have 1/2 little m plus capital I cm over r squared times v squared. So we pull this r out, group it, or put it underneath the ICM, and then we have a relationship here. So what we can do is we can then solve for the velocity, solve for the translational velocity, which tells us how fast the object is rolling, and hence would tell us how the higher v, that means it takes less time to go from the top to the bottom. So we can solve for v relatively straightforwardly. It's just some algebra. We get that v, and I'm going to do some rearranging here, is 2mg r squared divided by I plus mr squared, and this should be ICM. So this is all to, let me write that just so it's a little bit nicer. ICM plus mr squared. All I've done is regroup. Yeah, h should be there. Hold on. Yeah. Let me think about this just for a minute. It should be mgh r squared. I just got to make sure that this is right. Okay, let me actually do. Now I actually have to do the algebra. So it's 2mgh over m plus I over r squared, and so yeah. Okay, so I'm just missing an h up here. That's all. mgh r squared. There we go. Good catch. Thank you. Yeah. Erase, please. I'm just gonna add that to my notes so I remember to fix it before I send out the lecture notes. Okay. Right. Okay. So that's what we end up with. And so let's think about this. So faster speed means it reaches the bottom faster. And what we see is that if the moment of inertia is bigger, then the speed is smaller, right? This is for a fixed mass, for a fixed radius, for a fixed size of our cylinder. The bigger the moment of inertia, the slower the object goes. And that kind of makes sense, right? If it takes more to actually rotate it, it won't be able to rotate as fast, because however fast it rotates, that translates to the speed. And so if it's rotating really fast, that's a lot of energy, and it only has so much energy to go, so it can't rotate as fast. So this is to say, if I is large, then we have that v is small. And so there's less translational kinetic energy, or the proportion of the total energy that is the translational kinetic energy is smaller. More of it goes to the rotational kinetic energy. That's precisely what's happening here, Lucas. More of the potential energy is being stored in the rotation of the cylinder than in the translational motion of the cylinder. So we can actually get a little bit more precise here. So just as a quick note, remember from last time we went over a whole bunch of moments of inertia of cylinders. The moment of inertia for a cylinder, for a hollow cylinder, actually this is true for any cylinder. For any cylinder, moment of inertia is proportional to mass times the radius squared. Now, that constant of proportionality differs depending on how the cylinder is configured. Like, for example, if it's a solid cylinder, that constant of proportionality will be a half. If it's a hollow cylinder, it'll be 1, and so on. And you know, if you change the density as you go throughout, it'll differ. And so actually what we find is V is independent of mass and radius. This is VCM. The way to see that is that I is something like, let's call it A. A is just, it's just a constant, right? If it's a solid sphere, it would be a half. If it's a solid cylinder, it would be a half. If it's a hollow cylinder, it would be 1 times mr squared. And so we can plug that in to VCM. This is for any cylinder. We would get 2mgh r squared over a mr squared plus mr squared. And so the mr squared are going to cancel out entirely. And so we get 2gh divided by 1 plus a. No, it does. This is assuming, this is for a cylinder passing through with an axis passing through the center of mass. So that is to say, the speed that the cylinder rolls down with only depends on how the mass is distributed in the cylinder. Is it all on the edge? Is it all in the middle? Is it somehow uniformly distributed, and so on? This A tells you how that mass is distributed in the cylinder. But importantly, it doesn't depend on the total mass. It just depends on how the mass is distributed. So that's why in the video with the video with Walter Lewin, that's why the mass, or like the material that the object that the cylinder was made out of, didn't matter, because all that does is it affects the mass. It doesn't affect the distribution. Similarly, the size of the cylinder didn't matter, because again, all that affects is the radius, not the distribution of matter. So there's an example you guys should take a look at in the lecture notes, and otherwise we're going to continue on to look at another example of rolling without slipping. So let's look at massless pulleys again, or rather, the point is we now have the tools to look at massive pulleys. Now that we have, or at least we can look at them to an extent. And we're not actually going to look at a pulley just yet. We're going to look at a slightly simpler case, which would be a spool unwinding. We're going to look at a falling mass unwinding a spool, which is similar to a pulley. It's just it only has one end. We will talk about pulleys, though, after this example. So the picture here is, let's say you have a spool of, say, rope or chain or whatever, and there's a mass attached to it on one end. This spool of rope has some radius r, and the spool itself has mass m. So it's like a big wooden disc with a whole bunch of massless rope on it. Again, we are assuming that the rope is massless here. And let's say that this starts off at 0, and then you let go. Now, neglecting friction on the axle and so on, the mass is going to drop, but the speed that it drops at will be affected by the mass of the spool itself. Because if the spool is really heavy, it'll take a lot of force, a lot of energy to get it spinning, because it'll have a lot of, any amount of motion of the spool will have a lot of rotational kinetic energy. So let's look at, this is the before case. Then the after case is, say, the mass is, say, here. Say that it falls a distance h again. We'll call this y equals 0. We'll call this y equals h. And now the mass is moving down with some speed v. And again, the spool still has the same radius. It still has the same mass. So we might be able to ask the question, or answer the question rather, how fast is the block moving when it's fallen a distance h? Now, if the pulley or if the spool was massless, then it would just be standard translational kinetic energy, right? You'd set mgh equal to 1/2 mv squared, and you'd be done. Because if the spool is massless, then the rotation of the spool has no associated kinetic energy. But now that we're treating the spool as if it has mass, now the rotation of the spool, which is affected by the rate at which the block is falling, has kinetic energy. And so this would be another example of perfect rolling, because if say the mass falls a distance 2 pi r, i.e. it has traveled downwards by 2 pi r units, that means that the spool will have rotated precisely one full rotation, because the circumference, this is how much string was wrapped around, or rope was wrapped around the spool, that circumference is 2 pi r. So in order for the block to fall 2 pi r units, exactly one full rotation must have been unwound. And so this would be another perfect example of perfect rolling. So we can use that to solve our energy conservation equation. So again, we have initial kinetic energy plus final, or plus initial potential energy equals final kinetic energy plus final potential energy. Again, we're going to assume that the final potential energy is 0, the initial kinetic energy is 0, as per the setup that we have here. And so we can just do the same thing. We have mgh on the left, that's the initial potential energy. And then the kinetic energy, we have a block with that's just moving downwards. It has kinetic energy 1/2 mv squared. And then we have the kinetic energy of the spool itself. This would be 1/2 I of the spool omega squared. Now, perfect rolling gets us that omega is related to v. So what do we have? We have 1/2 mv squared plus 1/2 r squared. By the way, we're going to assume that the spool is, I'm doing 2 steps here. The moment of inertia of the spool is 1/2 m r squared, assuming that the spool is just a solid cylinder. And then we can plug in what omega is from the perfect rolling condition, v over r squared. So again, we can do some simplifications. We get 1/2 m plus 1/2 capital M v squared. The r's are going to cancel out, which is nice. So this is equal to 1/4 2m plus capital M v squared. And so what we get for our speed, this is the speed of the falling block after it's fallen a distance h, is the square root of 4 mgh over 2 little m plus big M. So again, we find that the speed of the falling block depends, in this case, it depended on the moment of inertia, and through the moment of inertia, the mass of the pulley. If the pulley is lighter, it will fall faster, right? Because M would be smaller, or 0, and so speed would be greater. So again, this is another example of potential energy being put in 2 separate places. One place is the translational kinetic energy of the block. The other place is the rotational kinetic energy of the pulley, of the spool. And so the heavier that the spool is, that means that for any amount of speed the block's moving at, the spool will have a lot, or will have more energy, because if the spool is heavier, it has larger moment of inertia. And we see that coming out in this equation, or in this result that we just derived. So again, linking another example, but this is the kind of thing that rolling without slipping can be really useful for. It can get you, it almost acts as a constraint. Remember when we talked about how does the spool fix an episode? Oh, we're just assuming it's like bolted to the wall or something. It's not floating. It's like bolted to the wall. Yeah, sorry if that wasn't clear. So this is just another example of rolling without slipping, giving us a constraint. And that's really what it is. Remember when we talked about constraint, it's something that doesn't come from Newton's laws or energy conservation or whatever, that is still a property of the system. So like the example that we first saw was telling us how the friction force was related, to the normal force. That didn't have anything to do with Newton's laws. That didn't have anything to do with, energy or anything. It was just a fact that we could measure. Here, we established from reasoning about the shape of a circle that the rolling without slipping condition gives us a constraint on the speed of one thing relative to the rotational speed of another. So let's do a third example of rolling without slipping. Or it's not quite rolling without slipping, but it's very closely related. Let's talk about a massive pulley now. And so remember when we first introduced this notion of tension and pulleys, one of the things that we had to use was in order for the, like a rope to transmit tension equally, so like the tension on one end of the rope was the same on the as the tension on the other. In order for that to be the case, I said something along the lines that the pulley had to be massless if it was going around a pulley. So now I'm going to show you how that works. So why is it? How does the mass of the pulley affect the tension on a rope? So we're going to drop our assumption that the tension is the same on both sides. And instead, we're going to have two separate tensions, and we'll try to figure out if they're different or not. So let's take, for example, we have a standard setup. We have a pulley, we have a block attached to a rope. Rope goes over a pulley. So we have M1 here. Let's use little m's. M1 and M2. And we have V1 is initially 0, V2 is initially 0. I'll just say stationary. So this is our initial setup. And let's say that this pulley has moment of inertia I. We're not going to go into details about what that is, but it's just something that's not 0. If the pulley didn't have mass, moment of inertia would be 0, because moment of inertia is basically, it's a number times the mass times the radius squared for cylinders, which most pulleys are. So let's see if I can do this well a second time. So we have our pulley. At a later time, the pulley or the block has fallen a little bit. Now everything's moving to the left at speed v, moving down at speed v. This thing's rotating at angular speed omega. Let's say that this this distance called x, which is also the same as this distance here. They both travel the same distance because they're still both attached to the same rope. So now we can analyze the system. So the sensible way to analyze the system is with energy conservation, but not quite the energy conservation that we've thought about so far. So let's talk about, let's kind of sidestep back up a little bit and talk about a situation that or use a method that we haven't used in a while. Let's apply the work energy theorem on the blocks. So the work energy theorem on the blocks only, not on the pulley. So the way that we can compute the total work done on the blocks is by computing the total work done on each of the blocks individually and then adding them up. So the work done on block 1, the work energy theorem on block 1 would just give us that this is equal to the change in kinetic energy of the first block. Now we know what the force is on block 1. This is some tension force, call it T1. There's also going to be a tension force upwards on block 2, by the way, and a gravitational force downwards on M2. So the force, remember, we can get work if assuming that the force is constant. We can get the work by just multiplying the force by the distance traveled. In this case, we can assume that this is it's not even an assumption, it's just true, that the force is constant in this case, and that's because the driver of the force is constant. This is the gravitational force is the only force that's external, that's truly external to the system. So all other forces are constant in this case. Anyway, that is to say, the work done is just T1 times x. The block's traveling in the x direction, and the force is the block is traveling to the right, the force is to the right, force has magnitude T1, block travels x units, force is constant, so we just get that the work done is T1 times x. And the change in kinetic energy, it starts off at rest and ends up at a speed v, so the change in kinetic energy is 1/2 m1 v squared. We can do the same thing for block 2, but block 2 is a little bit more challenging because there's two forces at play. But again, the net force is constant. So the net force would just be m2g minus T2. By the way, for the sake of this, this computation, we're treating up as negative and down as positive. That's the coordinate system that we're choosing here. So the work done, the block falls down a unit x. So this force is applied over a unit x, as is the upwards tension force, also applied over a distance x. So the work done is m2g minus T2 times x. And this is equal to 1/2 m2 v squared. And so what we can actually do is we can solve the second equation for t2 times x to give us m2 gx minus 1/2 m2 v squared. All right, I know that this is kind of roundabout, but we'll get somewhere that's useful. So the whole purpose of this analysis that we're doing is to see how the mass of the pulley will affect the tensions. We want to compare how T1 and T2 compare. If the mass of the pulley was 0, we've said that the tensions should be the same. So one way to check if they're the same is just subtract them. Subtract T1 from T2 and see if you get something that's 0 or not. If it's not 0, then you know the tensions aren't the same. If they are 0, then the tensions are the same. So let's take the difference. So T1 minus T2, well, we have expressions for T1. We have an expression for T2, so we can relate them. T1 minus T2 would be equal to 1 divided by x. We'd have to take the difference of these two things and then divide through by x. Or I suppose we could divide through by x and then take the difference. It doesn't matter. Times 1 over m1 v squared minus mgx plus 1/2 m2 v squared. Now we can rearrange this scenario or rearrange this equation to write it as 1/2 m1 v squared plus 1/2 m2 v squared or plus minus mgx. But look at this grouping. This is the total kinetic energy of the blocks. Or rather, it's the change in the kinetic energy of the blocks. And this is the change in potential energy of the blocks. All I did was I just subtracted this. I subtracted T1 from T2. So solve both of these equations. Solve this equation for T1 and solve this equation for T2, and then subtract the two. No, we're not ignoring the 1 over x. It's just there. It's a 1 over a distance. So this equation gives us that T1 is equal to 1 over x times 1/2 m1 v squared. This equation gives us that T2 is equal to 1 over x m2 gx minus 1/2 m2 v squared. Yeah, it's T1 times x. Yeah. So now you can just subtract this equation from this equation. Yeah, that should be an m2, sorry. Right, okay. So this is the change in kinetic energy of the blocks. This is the change in potential energy of the blocks. And so but remember that's not the whole thing, right? So if we wanted to just treat the block as if we just wanted to treat our system as just the blocks, then there would be perhaps some external work because there's other stuff involved in the system. In particular, there is this pulley, and the pulley could potentially be doing work on the system. However, we could instead just treat the whole thing as our system. So treat blocks plus pulley as the system. If we do that, then we can apply the work energy theorem. There's nothing external to the system. Oh, we're also including the Earth here, by the way, plus Earth. Right. There's nothing external to the system, so there can't be any external forces. And so that should be equal to the change in kinetic energy of the blocks plus the change in kinetic energy of the pulley plus the change in potential energy of the blocks. I mean, there would be a potential energy change for the pulley, but it's 0 because it's not moving. And so the important point is that we have that delta KE of the blocks plus delta PE of the blocks plus the change in kinetic energy of the pulley should be equal to 0. Now we know that what this change in kinetic energy of the blocks and the change in potential energy of the blocks is. That's equal to T1 minus T2. So we can actually move this over to the other side, or yeah, let's move that over to the other side. Well, okay, we'd have to be a little bit careful. We should move that over to the other side first. Yeah, so what we end up with is 0 equals x times T1 minus T2 plus the change in kinetic energy of the pulley. Remember, all we care about is the difference we care about the difference in the tensions. And so what we're left with is that T2 minus T1 is equal to 1 over x times the change in kinetic energy of the pulley. And we know the change in kinetic energy of the pulley. It's rotational motion, so it's 1/2 I omega squared. So T2 minus T1, remember, this is the difference of the magnitudes of the tensions. This is 1 over x times 1/2 I omega squared, where this I is the I of the pulley, that omega is the rotational speed of the pulley. Okay. Oh, and by the way, it's just 1/2 I omega squared rather than a difference because the initial kinetic energy is 0 because it starts off at rest, right? So this is positive, right? The final kinetic energy of the pulley is positive. The initial kinetic energy is 0, so the change is positive, which tells us that T2 is greater than T1. So with a pulley being involved, and in fact, this tells us precisely how much bigger T2 is than T1. It's this much bigger. So if I was 0, if the pulley had 0 mass, then T2 would equal T1. But because the pulley generally has mass in real life, T2 has to be bigger than T1. And a way to see this, by the way, is use use Newton's third law here. If this chunk of the rope, let me actually draw a picture here, draw a blown up picture. There we go. So we have a tension force this way, that's T1. So that gives this a tension force this way, Newton's third law. Similarly, we have a tension force this way on the block, which gives us a tension force this way on the pulley. So if the pulley is going to rotate clockwise, this force ought to be bigger than that force. That's reasonable, and that's sensible, which is why we had to have that. Now, if the pulley is massless, you don't need any force in order to get something moving, because basically F equals ma. You can start something moving with 0 force. So you don't need T2 to be any bigger than T1. But because the pulley has mass, you need to be rotating it harder in the clockwise direction than in the counterclockwise direction. So there's one more type of energy that's associated with rotation that I think that we should talk about. And that is something that's not quite related to rolling without, oh boy. Oh boy, where'd it go? Okay, it's back. One more type of energy associated with rolling without slipping, or associated with rotation rather, not rolling without slipping. Yeah, I zoomed way out. What's the difference? So the difference comes from the pulley, right? The point is our assumption was wrong. Like it wasn't true that the tension is the same. And in fact, so what's happening is that there's some amount of tension that the second block is causing, and some of that tension is being used up rotating the pulley, and the leftover bit is used to pull the first block. Right. So let's talk about energy associated with an object swinging about a fixed point. And then we'll end it after we finish this. So you might ask the question, how fast? So let's say that we have a uniform rod, right? Initially it's horizontal, and then it swings down. Let's say it has length L, has mass M, and it swings down to a vertical position. How fast is it going by the time it swings down? We can actually use energy considerations there to figure that out. So we know that again, treating the system as our Earth plus the rod, our energy conservation, it looks like the change in kinetic energy plus the change in gravitational potential energy. That should be equal to 0. There's nothing else. So the question is what is the change in gravitational potential energy? Well, we know what the initial potential energy is. At least that's reasonable. We could just write it as like mgy. But what is it down here? Well, because some of the rod is higher up, some of the rod is lower down. So we need to figure out a sensible way to figure that out. So the way that we figure out the change in gravitational potential energy is we break it up. So we know we can break up the rod into a bunch of chunks and then add all of those changes in potential energy and then add that together. So this would be, say, m1g delta y1 plus m2g delta y2. And these are for all of the different chunks on the rod, right? Plus dot, dot, dot. And so we can actually rearrange this. We can do some algebra. We get capital Mg times little m1 delta y1 plus little m2 delta y2 plus dot, dot, dot divided by capital M. So I just multiplied and divided by capital M. So these would cancel out. It will be the center of mass. And so this term here, that is the change in position of the center of mass, because m1 y1 plus m2 y2 dot, dot, dot divided by m is the center of mass. So if you stick a delta there, it's the change in position of the center of mass. So this is capital M, mg, delta ycm, which is just to say that the force of gravity, and this is just generally true, this is just an example of such a phenomenon, gravity only cares about the location of the center of mass. The gravitational potential energy only depends on the location of the center of mass. And in fact, the place in space where you can treat gravity as acting from is at the center of mass. Gravity acts from the center of mass. And where a force acts from will become relevant soon. And this place, by the way, this is why, basically because gravity acts uniformly on everything, on every chunk of mass. And so the average location of where that gravity is acting from can be treated as the center of mass. That's also why the center of mass is often called the center of gravity. Right. So then what about the kinetic energy? Well, okay, so we already figured out what the change in potential energy is. It's just the change in, it's mg times delta ycm. Well, the change in kinetic energy, we already know how to handle that. We can just treat it as if it's an object rotating about a fixed point in space. We already know how to handle that. It's just the change in kinetic energy about a fixed point, which is just 1/2 times the moment of inertia of the object about that fixed point times omega x squared minus 1/2 that same moment of inertia about that fixed point times omega I squared. And this omega I squared is 0. And we know what the moment of inertia is about the end of a rod. That was something that we can calculate. It's 1/3 times ml squared. So this is 1/2 times 1/3 ml squared omega squared. So when the rod reaches the vertical position, when that happens, we know how far the center of mass has moved downward. It's moved exactly downward half the length. That's the center of mass, presumably. So this distance would be half the length, right? We have that delta ycm equals minus L/2. So we're almost done. We have 1/6 ml squared omega squared. That's from the change in kinetic energy, plus mg times minus L/2 equals 0. And so we can just solve. We get that omega is 3g over L. And that's the speed. That's the angular speed that the rod will be swinging at by the time it gets to the bottom. And then you could figure out, how fast is it swinging when it's a 45-degree angle and so on. But the point is we can use our rotational kinetic energy tools combined with our translational kinetic energy tools to solve problems. A whole bunch of real life problems, because real world things spin, they have extent, they're not massless, and so on. So I'm going to end lecture there.